Chapter 8, DC circuits. DC circuits. One of the things that you need to understand about this chapter is it's the concepts that we're going after. We want you to understand the basic concepts. You're not going to make a lot of money necessarily going out and working on circuits like this in industry, circuits that are made up of a power source and a bunch of resistors. But what this is designed to do is to show you an approach on circuit analysis. We are going to use circuits that contain a bunch of resistors in industry, and those resistors are going to be used to establish voltage operating points around transistors or other semiconductor devices. So, although you're never going to go out and necessarily work on circuits exactly like this, you have to absolutely, positively understand the steps and the competencies of circuit analysis as it pertains to DC circuits. Okay, that goes without saying. And quite frankly, we've already talked about these concepts. This is just the chapter where we pull it all together. After completing this chapter, you're going to be able to solve for all, and let me emphasize the words all, unknown values. That means voltage, current, resistance, and power. Always solve for everything. Because if you know everything, I could never ask you anything that you don't know, because you know everything. In series circuits, parallel, and series parallel circuits. Understand the importance of voltage dividers, and design and solve for all unknown values in a voltage divider circuit. We are going to spend time on voltage dividers. Some of the stuff I'm going to blast through, but voltage dividers are something that I'm going to spend some time on the board here to make sure you got a handle. Because quite frankly, the book is okay, but the author really drops the ball with voltage dividers. He pulls a couple numbers out of the air that I still don't have a clue where it comes from. So I'm going to show you how to approach that. As you know, a series circuit is a circuit that provides only one path for current flow. The simplest example of a series circuit, you ever have those holiday lights, the Christmas lights that a bulb burns out and the whole string goes out? It's a series circuit. Because the filament of one bulb interrupts the flow of current to all the other bulbs. It's a series circuit. If you've got a string that one bulb burns out and maybe 10 other bulbs go out, what does it tell you about those 10 other bulbs? They're all in series. The whole string may be a combination circuit, but that individual section that went out is in series. So there's a lot of lessons behind looking at festival lighting and when it goes out, what exactly is taking place there. Factors governing the operation are the same current flows through each component. Literally the same current. The same electrons. They only have one path to go. That's from negative to positive, so they have to travel the entire route. Total resistance in a series circuit is equal to the sum of the individual resistances. Right? This is what, chapter 3, 4 review. Right? You got resistance, you add it up in series. Always additive. And that includes the resistance of a bad solder joint, the resistance of a bad splice. Remember how I said the power company, the voltage company, will actually use thermography and look and say, wow, we got a splice up there and it's generating a lot of heat. We got to shut that section down and replace that, because it shouldn't be generating any heat if it's a good splice. The total voltage across a series circuit is equal to the sum of the individual voltage drops, meaning total voltage is equal to voltage across component 1 plus the voltage across component 2 plus the voltage across component 3. This is a review. This is the same thing you could quote me, right? I love it when you quote me, right? Voltage rise equals voltage drop, okay? So here, voltage rise, ET, or VT if you prefer, equals voltage drops. ER1, ER2, ER3, those three voltages better equal what I put into the circuit. If not, you got a problem. If you find where the missing voltage is, you probably found the problem. Where was the missing voltage? Where was it? Oh, it was in a bad splice. Oh, okay. You fix that problem, boom, you're up and running. The voltage drop across a resistor in a series circuit is proportional to the size of the resistor, meaning the bigger the resistor, I'm talking about in ohms, I'm not talking about physical size. The more ohms, the less current. The more ohms, the higher the resistance, the bigger the voltage drop across that resistor. I always think of a resistor. Remember how I used Seattle traffic flow as an analogy? Right? A big resistor is like a big accident. If you just got a fender bender, is that going to slow the traffic down? Yeah. Fender bender, they pull over the side, people stop, slow down, look or whatever. Right? You got a 5-car pileup. It's a big accident. That's a big resistance. A big resistance is going to create, I gave it away already, a big backup. A big backup is a big difference in potential. A bunch of people here that want to get to work and a bunch of people here on the other side of the freeway an empty freeway basically. That's a big difference in potential. Okay? I love flying in my airplane over traffic jams. As a matter of fact, being a pilot, owning an airplane, being stuck in a traffic jam drives me freaking nuts. Like, why am I stuck in this traffic jam? But from the air, it's so obvious where there's an accident or a problem because all the traffic's backed up and then just a few cars are making it through. Difference in potential, big resistance. Make sense?
In the book, it says ET is equal to ER1, equal to ER2, equal to ER3.
It's a mistake. That's for parallel. You sure that's not parallel you're looking at?
Total voltage across the series circuit.
Bzz, typo. Typo. Yeah. Total power in a series circuit or parallel circuit or complex circuit. Power is additive. PT is equal to PR1, PR2, PR3, PR4. Just add up all the power. And that's going to give you your total power. The bottom line. You want the bottom line or you want the BS? Bottom line. In a series circuit, the most important thing to remember about a series circuit is current is constant in a series circuit. Period. The second most important thing to remember about a series circuit is also synonymous with voltage divider. When I say series circuit, I want you to think current's constant, and I want you to think voltage divider. That's just how I want you to look at them. And if you're not looking at them that way, you ain't looking at them right. Houston, we're going to have a problem. Okay? Those are the most important things. I'm going to have you repeat that back to me in the future. Do not deceive me. Okay? Remember that stuff. The most important thing in a series circuit is current is constant. Why is it constant? It's only got one path to flow, so it better be constant. The second most important thing about a series circuit is also known as, right? AKA, like in police lingo, AKA, also known as a voltage divider. Voltage divider. In this particular circuit, I look at it, and yeah, I've been doing this since puberty, but I look at this, and what do I see? I see a voltage source and 3 voltage drops. Voltage rise and 3 voltage drops. 3 loads. I don't know what they are, but I know these loads are connected in series. And I know that all the current that flows out of the negative terminal of my voltage source has to travel this complete path. No place else for it to go. So the current's going to leave the negative terminal of the battery. It's going to make this corner, 90-degree corner at the speed of light. This is cool stuff, ain't it? The speed of light. Come on down through here, the back stretch, hit resistor 3, and create a voltage drop, a difference in potential. Current's going to finally make it through that obstruction. Another 90-degree corner at the speed of light. Come up here to R2. It's going to create another voltage drop because there's another obstruction. There's more resistance here. Current's going to continue on, another 90-degree corner through R1, another voltage drop. This voltage drop, this voltage drop, this voltage drop have to equal this voltage rise. If anything's missing, you got a problem. Find where it's missing, and you found your problem. Power, additive. Resistance, additive. What else is there? So anytime you've got, the other way I want you to look at it is anytime you've got one way into a circuit and one way out, what does that tell you? It's a series circuit. It's a series circuit. Because I cannot show you every possible series circuit ever invented. If you've got one way in and one way out, it's a series circuit. Even if it's one component. One component, could that be series? Yeah. One way in, one way out, it's series. Tight? Tight. To solve for values in a circuit in order, the first thing I recommend you do is try to solve for that total resistance. Once you determine RT, total resistance in the circuit, then try to solve for total current in the circuit, IT. Once you know IT, then you could determine what your individual voltage drops are, right? So solve for your total resistance. Total resistance with your total voltage will show you how much current you're allowing into this circuit. Current flowing through the circuit encountering the resistance. V is equal to I times R. The total current, the same current that travels the entire path, times the amount of resistance there is in a circuit. So this is going to drop a portion of that voltage. This is going to drop a portion of that voltage. This is going to drop a portion of that voltage. These three portions better equal the voltage that's put into the circuit.
In regards to the slide previous to this, which is
this one?
the 3 steps,
Yep.
it doesn't say on the slide series or parallel. So these, will they primarily cross over between the 2 applications?
Yeah, but I gotta warn you, this here is just like generic. This is like generic.
Sure.
And the thing of it is when you get out into industry or in lab, I may give you this, I may give you this, I may give you this, but this is encased in epoxy. You can't even get to it. You can't even get a part number off of it. You can't even take a reading of it. So you're going to have to use these laws and say, well, sheesh, I remember Joe said that this is equal to this plus this plus this. I know what this is, I know what this is, I know what this is, but I don't know what this is. So then you could say this, the remainder is equal to this. And it's a safe assumption because you're using a law, Kirchhoff's voltage law, basically to determine what the unknown is. And if you're using a law in industry to figure out what part you need to buy, whose money you need to spend, it's a pretty safe assumption. I mean, it really is. So that's why we're teaching you this. So don't necessarily use this as a checklist and like, oh yeah, I took copious notes. I listened to what Joe Grenick had to say in lecture. I went home this weekend to try to do my homework and it didn't work because I couldn't determine total circuit current because I didn't know what this value was because Joe didn't say sometimes we might not know what this value is or we need to find it on the internet off of a data sheet from a manufacturer. So the bottom line I want all of you to realize with these circuits and analyzing these circuits, you always need to find at least 2 bits of information. If I only give you 1 piece of information, you're not going to be able to get very far. But if you could extract 2 bits of information, then you could remanipulate these 3 to suit your needs as long as you get the right answers. Make sense?
Absolutely.
Okay. Parallel circuits. I might as well get the cat out of the bag right from the get-go. Parallel circuits, the most important thing you need to remember about a parallel circuit is voltage is constant across a parallel network. Voltage is electrical pressure by being constant across a parallel network. What am I talking about? I'm saying that that voltage will be constant across all components that are connected in parallel. Your house is wired in parallel. The freaking voltage coming out of the outlets better all be the same. If not, you got a problem. You got a problem. Voltage is constant across a parallel network. Most important thing you need to remember. So when I say that, what's the most important thing about a parallel circuit? Like church, you all repeat after me. Voltage is constant across a parallel network. Okay? The second most important thing about a parallel circuit is that a parallel circuit is also known as, police lingo, AKA, also known as what? If a series circuit's a voltage divider, what's a parallel circuit? It's a current divider. It divides up current. Some of the current goes one path, some of the current goes the other path. Remember the Seattle traffic pattern last week? Was I here with talking to you folks about that, or was it somebody else? Was it a dream I had? I had a dream. It was about current. And that's what it is. So some of the current's going to take the 90, some of it's going to take the 520, some of it's going to take the north end of the lake, some of it's going to take the south end of the lake. Make sense? I've been a commuter for 20 years. I know Seattle traffic. I've gotten out of here and gotten on I-90 and driven eastbound to get to Tacoma, to Highway 18, just so I could avoid traffic. So I know a little bit about traffic. Look at these circuits like that. Factors governing the operation of a parallel circuit, the same voltage. The same voltage. Not an equivalent voltage, the same voltage exists across each branch of the parallel circuit and is equal to that of the voltage source. So literally, this is what we're up against. Total voltage is equal to voltage cross component 1. It's equal to voltage cross component 2. It's equal to voltage cross component 3. It's not only mathematically equal to, it's the same pressure. I'll show you in the schematic. Same pressure. And that, in and of itself, will help you solve problems. If you know something's in parallel, you could assume, if it's connected in parallel, I should have the same voltage across that. Well, sheesh, the thing's still not working, or it's working kind of goofy. It's hard to get to. Well, sometimes you have to remove that access panel, go in there and take the reading. Holy cow. Everything else in parallel is at 12 volts. This is only at 9 volts. I'm missing 3 volts. You find the missing 3 volts, you found the problem. It's that simple. One of the most powerful tools. How many of you here like tools? I got tools. I got like every tool known to man in my garage. Just ask my wife, she'll tell you. Okay? I like tools. One of the most powerful tools in your box is this stuff right here. The second most powerful tool you're going to have is the digital multimeter. Because the digital multimeter is going to allow you to get out there and find the missing 3 volts. You find the missing 3 volts, you found the problem. You found the problem, you save the day. You save the day, you hit your boss up for a raise, he gives you a pink slip, cut you loose. No, just kidding. You get a promotion, life is good. You make so much money, get married, start a family, get a girlfriend on the side, it's all good. I don't mean that. The current through each branch of a parallel circuit is inversely proportional to the amount of resistance of the branch. I is equal to E over R. I is equal to E over R. So that means, because R here, it means E over R, right? E over R. We use the slash here. But that means that this is on the bottom of the slash. So whatever we do to R is going to have an opposite effect on I. We call that an inverse proportional relationship. An inverse proportional relationship. So if resistance increases, current decreases. Bigger accident, less flow of traffic. Smaller accident, traffic flow increases. Plain and simple. So keep that in mind. The value of least resistance in a parallel circuit will have the highest current flow through it. The total current in a parallel circuit is the sum, literally the sum of the individual branch currents. That's why we call parallel circuits current dividers. Thank you. Current dividers. The reciprocal of the total resistance in a parallel circuit is equal to the sum of the reciprocals of the individual resistances. This is a fancy way of saying when we put resistors in parallel with each other, we actually add up the reciprocals. We add up the conductance of those paths, not the resistance of those paths. And the conductance of those paths literally is the reciprocal of the resistance. And that's what Siemens came up with, right? That was his whole trip. The other formula that I want you to be aware of, and I know some of you are reluctant to use it, it's the product over sum formula. If you've got 2 resistors or 2 resistances in parallel, use the product over sum formula. Product means R1 times R2 divided by the sum, R1 plus R2. And it's a real easy way. I mean, it's what's the, you got a 1/2-inch nut that you need to get loose. You could either use, the box end wrench, or you could use your teeth. Use the easiest tool. the easiest tool is the product over sum formula. Well, that's another formula we got to memorize. Don't memorize these formulas. Use them and learn them. Do you understand the difference? Memorizing stuff never worked for me. I mean, that's always my fear that I'm going to get pulled over. That's why I don't drink and drive, because like I get pulled over even if I haven't been, or you know, if I'm not totally under the influence, they're going to ask me to do the ABCs, and I'm probably going to screw that up. They're going to throw me in the hooskow because I don't know my ABCs, because I never really memorized them. I kind of like learned them. Saying backwards? I'm going to have you do that crap. I can't freaking do that. What the heck are you doing? While hopping on one foot, you know, recite the alphabet backwards. No, man, officer, with all due respect, let's see you do that. Huh? Jeez, you're killing me. Total power consumed in a parallel circuit is equal to the sum of the power consumed by the individual resistors. No mystery here. We just talked about it last chapter. Power is always, that's beautiful.
Hey, what were you saying about the product sum formula? When you can only use that in a parallel circuit?
Correct. If you only have two components in parallel. Two or more, you got to use your favorite formula. The reciprocal of the total resistance in parallel is equal to the sum of the reciprocals of the individual resistances. A lot of people like that one more than mine. Mine is only good for two. Also with that, don't forget your thumb rules. Remember your thumb rules? Right? If it's equal resistance, you simply count up the number of resistors, that value of resistance, and divide it by that number. If I have 4 100 ohm resistors in parallel with each other, what's the total resistance? 4 100 ohm resistors in parallel with each other. 100 divided by equals 25 ohms of resistance. The other thing for resistors in parallel, the total resistance will always be less than the value of least resistance. It'll always be less than the value of least resistance. Thumb rules. Okay? You pay attention to those thumb rules, your GPA is going to increase drastically because you're going to have something to check yourself against. I don't know if I used the right formula, but I remembered you always said the value of least resistance will be less than the value of least resistance. My answer meets that. I'm comfortable with that answer and stick with that answer. Power is additive. It's a parallel circuit. Remember how we said voltage is constant across a parallel network? That's because this electrical pressure being exerted by this source is distributed equally across these three loads, period. It's the same. It better be the same. If it's not, we got a problem. If it's not, we got a problem. Where's the missing voltage? This is how your house is wired in parallel. The outlet in your bathroom better have the same voltage across it as the outlet in your family room, as the outlet in your garage. If not, it's not wired properly. Something's up. I got a big circuit like this at home because I do everything big. That's how I roll. I made some significant improvements to my backyard about 10 years ago. My backyard used to come out and it used to drop off a hill, and it was just an unusable backyard. I wanted to like do stuff back there, you know what I'm saying? You know what I'm saying? So I was looking at, I had to build a retaining wall, talking big bucks to put in a nice retaining wall. So I was looking at different options, and I like to utilize the resources that are available to me. So I have a good friend of mine that worked for the railroad, Burlington Northern, and I said, hey, you know, you guys use those railroad ties. You know, what are the chances of getting some of those railroad ties? You know, like, you know, what are you talking about? Well, like a truckload. You know, those are hard to come by, Joe. You know, it ain't what it used to be. You know. So for like 3 years, I kept hitting him up for railroad ties and wasn't getting anywhere. And you know, we had a great relationship. And finally, he said something. He was kind of hitting around about going for an airplane ride. You know, it's hitting me up for an airplane ride. And finally, you know, I'm not the quickest study, the smartest guy out there, sharpest tool in the shed. And I finally like, oh, I get it. So I gave him a call, like, hey, Larry, what are you doing Monday night? You know, want to go for an airplane ride? I picked them up in Arlington, and we went out over the Cascades, beautiful sunset, whatever, landed, right? That Wednesday, my cell phone's ringing. Hey, Joe, still want those railroad ties? Yeah. Well, I got clearance not only to give you the railroad ties, but I got clearance to use a Burlington Northern crane to load them on a truck for you, okay? You just got to get the flatbed. So I went out and rented a flatbed. I drove literally. It was funny, it's Burlington Northern, but it was a yard up in Burlington. So I had to drive all the way up there. He loaded them on 148 ties. Long story short, I built a beautiful retaining wall. Actually, I had a former student of mine that was an engineer. He designed the wall for me, did the prints and everything, built this wall, and landscaped it. Beautiful. So now I have a backyard. My neighbors, they weren't digging it, because now they're looking at like, he's got a perfect yard, and we still, just like a wall, railroad ties. Funny part of that story too, I built that by hand, 148 ties. I don't know if you've ever picked up a railroad tie. They are heavy. I built that by hand, backfilled it by hand with a wheelbarrow, gravel, drainage, by hand. You know how much weight I lost that summer? 0. Probably had something to do with the pizzas and beer I was consuming while I did it. But anyway, what I wanted to do is when it was all landscaped and everything, in the process, before landscaping, I wanted to put in low voltage lighting around the perimeter. So like the goofy lights you stick in, and but I wanted to put in conduit. I wanted to do this right. And as a pilot, I kind of wanted almost to look like a runway, and an airport. The lights around the periphery. So I used these low voltage lights. I had a big power supply in my garage and an equipment rack. Dug conduit all the way back. Did my calculations, and the other thing about calculations, determining what size wire you should use. The kind of wire that I use is the kind that falls off the back of a truck, and the kind that contacts provide me with. So I went with this gauge wire. It was a little bit substandard, but I figured, the math kind of works out and it's kind of good. So I've got all these low voltage lights, and ironically, it came out nice. Came out really, really nice backyard. But I could tell. If I brought you back there, you probably wouldn't even notice it. But I could tell which light is the furthest from the power supply. Just looking at it. And it kind of bothers me. It doesn't bother me enough to rip up the conduit and pull new cable, okay? But I know. I know by looking at it. And what does that tell me? That tells me that the load furthest down the line is not getting the same voltage as the load closest to the source. And gradually, as you get further away from it, you just notice a little difference in illumination.
But shouldn't voltage remain the same in a parallel?
Yes, that's my whole point.
Length of
Why doesn't it?
copper is resistance. So at the longest distance, you just need a different bulb that's more efficient.
I needed to use basically a heavier gauge of wire. In doing that, if I had done that, then I could, there's ways I could fake it. Soldering, what are you doing out there? I'm soldering in resistors to these other lamps. Why to get it? My wife would probably finally really give me the boot, but it bothers me. It bothers me because I like doing things right, and I guess I did do it right, because you know how much that wire that I used cost me? Literally fell off the back of a truck. So, don't judge me. I have a friend that's a police officer. I asked him, I said, what's the whole deal like if I got something that fell off the back of the truck? He sat up and he's like, I'd love to cite the driver for driving an unsecured load. So. Anyway, so this is a parallel circuit. Now, yes?
You flooded the conduit with liquid nitrogen. Would that light be nice and bright?
That's one of the other things I was kicking around. Can I stick an inert gas in there and increase the dielectric properties? And she'd throw me out, man. She'd throw me out. And you know what? I know you find this hard to believe. Maybe you won't. But I actually have a nitrogen bottle at home. Doesn't everybody? And I don't necessarily use it for welding. Series parallel circuits. This is the easiest part of this entire chapter. Circuits that consist of both series and parallel circuits. To solve most series parallel circuits, simply apply the laws and rules of each type. There's no mystery. There's no silver bullet. There's no easy way for me to describe it to you. Use series formulas for the series parts of the circuit. Use the parallel for the parallel parts, period. That's all it is. That's all a series parallel circuit is. That's what it looks like. R2 and R3 are in parallel with each other. You got to solve for that before you could solve the total resistance. Because R2 and R3, one of the things that I like to do is identify these points right here. These are called nodes. I'm going to call this node A and node B. The resistance between node A and node B is equal to the parallel resistance of R2 in parallel with R3. I'd use the product over sum formula to determine what RAB is. Follow what I'm saying? RAB, the resistance between node A and node B. The total resistance in the circuit is equal to R1 plus RAB. That's what equals total current, or excuse me, total resistance. Total current can be determined by that. Once I know what total current in the circuit is, total current is going to create a voltage drop across this resistor. Total current is going to create a voltage drop across this resistance. The resistance I'm talking about is the resistance of AB, which is the combination of 2 in parallel with 3. Make sense? So once you do that, it's just easy to slice and dice. The worst thing is when you see, I mean, obviously we gave you some problems in the assignments in the book that are take time for you to solve. But the first thing you got to do is break it down. The other thing too is if I had a resistor in series with another resistor here, I'd need to solve for these two first because they're in series with each other, but in parallel with this. So then I need to solve for this section of the circuit, which is in series with this section of the circuit. So, a lot of students get frustrated and think there's a checklist they could follow or a protocol. No, you just got to pay attention to the individual laws and rules that we established, but there are no two circuits alike. One of the things that I've heard over the years of teaching here, I get a lot of new students that come, or quite frankly, a lot of people that are working in industry already, and they want to come in and they want to learn how to read schematics. Joe, if I come to your program, can I learn how to read schematics? Well, yeah, but we don't have a schematic reading class. There's no schematic reading class. And quite frankly, I wouldn't want to have a schematic reading class, even if I could fill the schematic reading class, because you wouldn't learn anything. What are you doing here by studying this? You're learning how to read a schematic. You're learning to differentiate between those sections of the circuit that are in parallel with each other and those sections that are series components. Later on, when we talk about transistors, right now, those of you in the full-time program did a component ID test today to be able to recognize different types of components. You're going to see what happens when we put a transistor, a diode, a capacitor, different components in different configurations. If I put a capacitor in series, all as it is a capacitor in series. It's still a series circuit. And everything that we've talked about this week still applies. There's going to be some things that are going to be a little bit different with a capacitor in the circuit. We'll cross that bridge when we come to it, but it's still a capacitor connected in series. And there's really only 3 types of circuits that you're ever going to deal with in your entire career. And that is series, parallel, and complex. So if any of you this week have been grunting, groaning, outside, weeping, gnashing your teeth, you know what? It's all right. Because once you master series, parallel, complex, there's nothing else I'm going to throw at you. There's nothing else that Peter's going to throw at you. Now that being said, we're going to have you looking at some complex circuits in the future. And you know what? You will deceive me. As much as you could pass this test on series, parallel, complex circuits, you're going to forget about it in the future. Because we're going to give you some schematic to read that's got some different components on it, or it's got some components drawn at weird angles or something, and you're going to get your freak on. And you're going to say, boy, they never taught me that. I don't know what to do. You know what you do? You fall back to the basics. The only circuits you're going to encounter in industry are series, parallel, and complex. And if it's complex, what laws do you use? Those of series and parallel. You just got to figure out which components are in series and which one are in parallel. I can't say it any stronger. If it's in series, there's one way in, there's one way out. If it's in parallel, that means there's interconnection of all the components. Make sense? Voltage dividers used to set a bias or operating point of various active electronic components. We use voltage dividers to create the voltages that turn on transistors and integrated circuits. They're used to divide a higher voltage to a lower voltage, and this process is often called scaling. Because what are we doing? Voltage rise equals voltage drop, or voltage drops. So voltage drops will always be a fraction or scaling of the total voltage that we apply to the circuit. Does that make sense? We're going to use Ohm's law to solve that. That's the current through a circuit. I'm not done with voltage dividers. Trust me, I'm not done. I'm done when the screen goes black. Then I'm not done when the screen goes black. Then I'm going to show you some stuff on the board. So sit tight. That's not my spiel on voltage dividers. Ohm's law, the current through a circuit is directly proportional to voltage across the circuit, inversely proportional to the resistance. Ohm's law, I is equal to E over R. Current division. Current is directly proportional to voltage across the circuit. If a voltage increases, current increases. If a voltage decreases, current decreases. The voltage drop is equal to the percentage of the dropping resistor to the sum of the dropping network. You know what? I'm giving you this formula. If you dig math, great. If this confuses you, just tune me out. Because everything could be solved with Ohm's law and Watt's law. If you dig math, this is another tool in your box. Let me show you how this thing works. If I want to calculate out my voltage drop across a load, across a resistor, this voltage is going to be equal to my voltage source multiplied by the voltage drop divided by the voltage total. Okay? Let's keep this really, really simple so we can understand how this formula works. If I've got two 100 ohm resistors, if I have two 100 ohm resistors in series with each other, and I want to know what voltage I'm dropping across one of those, I'm going to draw that. You know what I'm talking about? I should be able to use words because the test I give you, the quiz, is going to be words. So that's why I try not to draw too much on the board. I'll draw some stuff on the board, but I don't want to draw too much because Joe, all week you've been drawing stuff on the board and then you ask me a bunch of words. Okay? You got to pass the quizzes and they're words, word problems. Okay? But if I've got this, if I've got this, and I've got 100 volts, let's keep this real simple. Okay? What this formula is showing me is what is our drop here, V drop is equal to voltage total times R drop over R total. Okay? So let's take a look at that. Voltage total is going to be 100 volts times our drop, which is one of these voltage drops, whichever one you're trying to calculate for. Let's say it's this one. It's going to be 100 divided by, what's my total resistance in a circuit? 200. Okay, what's 100 divided by 200? What is it? 0.5. 0.5. What does 0.5 mean? What percentage? Half. It means 50%. So 100 times 50% equals what? 100 divided by 0.5. What does it equal? 50 volts. We could do this one in our head. That's why I want you to do this in your head so you understand the formula. You understand how the formula works? So if you know what this value of total is, and you want to calculate out, let's say that I went ahead and I changed this now, that this is, this is 500 ohms, right? And this is 100 ohms. And I'm asking you what voltage is going to be across this voltage drop here. 100 divided by 5, basically 1/5. 1/5, right? What percentage is 1/5? 2, 4, 6, 8, 10, 20%, right? So that means 20% of my voltage is going to be dropped across this. If 20% is being dropped here, actually no, right? Because this is 100 over 6, 600. So what percentage is that? I was off on my math, I'm sorry. You guys were buying it, man. I want to be your banker.
6%.
What's 100 divided by 600? Because total resistance is 600. 17. So basically 17% is going to be dropped right here. 100, 17 volts is going to be here. The remainder is going to be, where's the remainder voltage going to be dropped? This is an easy question. Right here. It's got to be. Because this plus this has to equal this. Does that make sense? So this is just another formula for those of you, the math addicts. Want another tool? I like tools. Just ask my wife. Got every tool, right? This is another tool for you. So if I'm giving you, I could sit here all day long and tell you how much voltage is dropped here, how much is here. It's a lot easier to use this formula. Although you could calculate the same thing using straight Ohm's law. It's just going to take you a little bit longer to get to the answer. Make sense? All right. In summary, a series circuit provides only one path for current flow. Series circuit formulas include IT is equal to IR1, equal to IR2, equal to IR3, et cetera, et cetera, et cetera. RT is equal to R1 plus R2 plus R3, et cetera, et cetera, et cetera. Voltage. A series circuit is also known as a voltage divider. So therefore, the sum of the individual voltages must equal source voltage. I is equal to E over R. Well, that's Ohm's law. Power is additive in a series circuit. Power is additive in a parallel circuit. A parallel circuit provides more than one path for current flow. Parallel circuit formulas include IT is equal to IR1 plus IR2 plus IR3. The reciprocal formula for resistance. Voltage is constant across a parallel network. Again, I is equal to E over R. If you want to calculate out how much current is flowing through an individual path. And power total is equal to PR1 plus PR2 plus PR3, et cetera, et cetera, et cetera. Series parallel circuits are solved by using series formulas for the series parts of the circuit, parallel formulas for the parallel parts of the circuit. We talked about voltage dividers, more to come. And we talked about current division, the process of current division in a parallel circuit. Any questions on this? Okay, let's talk about voltage dividers. Kind of get emotional when I talk about voltage dividers. It's kind of like your first real circuit that really does something. Trust me, it'll be good. We're going to need some help, though, because we got some electronic experts in here. We're going to need some help. What kind of a circuit would I use to divide voltage? Series. You got 3 to choose from. Multiple choice answer. Series circuits, parallel circuits, or complex circuits. The correct answer is ding, 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 series. Okay? So a series circuit is also known as a voltage divider, right? Y'all believe me? Okay, so let's go ahead and draw that. This is a voltage divider. Any questions? Unfortunately, this is a voltage divider, but unfortunately, this isn't going to do much for us. This will do a lot for us, but if we effectively want to use it, it really can't be represented like this. Can't be represented like this. First of all, we got to ask ourselves, why would we want to divide up voltage? We want to divide up voltage, like I said in here, to power transistors, to power integrated circuits, to power different types of loads, to power different types of devices. Make sense? Okay. So let's say, as an example, that I have a 48 volt power supply. This is a big rack-mounted power supply that sits there and drones and puts out 48 volts DC. But I've got some different appliances that I want to power from it. Okay? One of the devices that I want to power from it is a 12 volt radio. A simple 12 volt radio. Okay? And that 12 volt radio is a citizen band radio, CB radio. So what I need to do is I want to connect that radio to this resistor right here and have this resistor produce 12 volts across it. So when I go out here and connect my radio, which I'm going to represent, anybody know a symbol that I could use to represent a radio? What's that? R. Yeah. Yeah. There's no special schematic. What I'm going to do here is I'm going to draw a resistor, and that represents the load that a CB radio has. And I'm going to connect it in parallel. Do you agree that that's in parallel? So whatever voltage is here is going to be right here. Okay? When I did this, I just changed the dynamics of the circuit. I just changed the dynamics of the circuit. What I just did is I just loaded the voltage divider. So we're going to call this a loaded voltage divider now. And quite frankly, a voltage divider in and of itself, without any loads connected to it, it's kind of stupid. So you guys, if you had read ahead and you really had mastery of it when I'm showing you the voltage divider, you could have said, Joe, that's stupid. What are you going to do? Just put 3 resistors, divide the voltage? What good is that? Okay? What you got to do to make it viable is connect a load to it, a loaded voltage divider. This is a real circuit. We're really going to do something here. We're really going to power a CB radio. Okay? So, to figure out, we know that this is 12 volts because the manufacturer said this is a 12 volt CB radio. You could plug it in your cigarette lighter, you could wire it into your car, and you too could be breaker 19. Make sense? So we know the voltage is going to be 12 volts. The other piece of information that is critical for us is we have to know how much current is required by the CB radio to operate properly. So what we're going to do over here, okay, P, I, V, okay? I know that the CB radio, right, a typical CB radio is about 5 watts. And I know that CB radio, because I got the box, and the salesperson at Radio Shack, we know how smart they are, said I could wire it up into my car. It's a 12 volt system. Okay? So this is going to be 12 volts. So how much current is going to be required to power that radio when I key the microphone and I broadcast out 5 watts? What's the and that's by the way, that's the maximum you'll ever consume in a CB radio. If it's a 5 watt radio, the maximum you're ever going to consume is when you're transmitting. If you're just receiving, that doesn't consume much energy at all. It's when you key that mic and transmit that you're going to start consuming the most power. So I'm thinking worst case scenario here. Okay? So all we need to do here, right, with your calculator, go 5 divided by 12. What did I come up with? 0.42, rounding off, right? 0.411, 0.41666666. Right? That's what I got. Everybody get that? Everybody see how I came with that? Okay. That's assuming the radio is 100% efficient. You know what I mean? Like every ounce of current is going into generating that, which there's going to be losses. How do I know there's going to be losses? When I use the radio, it's going to get hot. All that energy is not going to get out the antenna. If you get that working, you get all the energy getting out the antenna, give me a call. I have my attorney contact you. I personally fly you to Bimini. I'll set you up. Pour you your first cocktail. Okay? I'll set the tab up for you. So what I'm going to do with this, just for the case of example, is I'm going to round this. Generally speaking, a CB radio is going to take a minimum of half an amp at 12 volts. A minimum half an amp, and probably it's going to be even more than that. But in order for it to transmit out 5 watts, you see the math. Does everybody see the math? Okay. So I am going to assume that this here is 0.5 amps. So we know everything about the CB radio now. It's a 12 volt, 5 amps, 5 watt radio. I feel pretty good about it. We could calculate out the internal resistance of it if we wanted to. I don't see the benefit of doing that now. We don't need to do that right now. Make sense? Okay. Voltage divider. voltage divider. I've got another device. And this other device that I have is, by the way, we're not going to put this in your car anymore. We're going to put this radio, CB radio, on my boat. Why I want a CB radio on a boat, I do not know. It's a power thing, man. I want to talk with truckers, so I'm going underneath the bridge. Ha ha, you're stuck in traffic, I'm going underneath it. Ha ha, I'm on my boat. Okay. I'm going to install a radar system. And the radar system that I could represent with a resistor is going to be connected across these two resistors. The voltage of my commercial radar system is 24 volts DC. And it puts out 200 watts. How much current is going to be needed to go through this device in order for it to transmit out 200 watts? Again, if you get confused, draw the triangle, P, I, V, 200 watts divided by 24. What do you come up with? How much? 0.12, 0.12?
120 milliamps.
How much? We got a big disparity here.
8.33.
That makes sense, right? If a half an amp can power a CB radio, it's going to have to be more than a half an amp to power a 200 watt transmitter, right? Yeah, even at double the voltage. So all I got to do here is power is 200 divided by how much? What's our voltage? 24. $8.33, and that assumes what? That assumes 100% efficiency. Do we get 100% efficiency out of this stuff? To be honest with you, if we're lucky, if some of this stuff operates at 80% efficiency, 20% of the energy gets consumed as heat. Okay? So just for the case of example, I'm going to say that this thing really, in order for it to work properly, is going to need 10 amps. And this might be what the placard data on the back of the radar says, or the manual says. Okay? But you understand that which one of these are real. If you do the math, this number could be good, this number could be good, and if that's the case, then we know that the answer is going to be 8.33 amps. But in reality, because of the losses, because of the property of resistance, we're probably going to be consuming really about 10 amps. Make sense? Okay. So, now what I have is a circuit, a viable circuit. And by the way, if I want 24 volts here, and I am getting this voltage across these two resistors, what voltage must I be dropping across this resistor right here? How much?
12.
Why 12?
Because it's double this, 12 volts.
Yeah, and I am connecting this radar unit in parallel. I love it when you talk that way. Parallel with these two resistors that are in a voltage divider network. Okay, so what we did is we just built a voltage divider, a loaded voltage divider. But we've got to analyze it now. We've got to analyze it. And this is where the author pulled numbers out of his backside, and he really didn't justify it, and I don't even know where that's coming from. That's why we're having this lesson. Question?
There's the other resistor up there that's hanging out by itself doing nothing.
It's 24.
It has to be 24, right, to get 48?
Why wouldn't that?
This, remember, this here, I bought this military surplus. This is a 48 volt power supply, okay? So it converts my ship's power to 48 volts DC.
That's still 48 volts at the end of it, it's all coming back together.
Yeah. So if this is 48 and this is 12 and this is 12, what's this got to be?
24.
24. Why?
Because you gotta drop it down to 24 volts.
0.
Come on, guys. Quote me what I've been quoting you.
Your drop has to equal the rise.
Absolutely, because the drops have to equal the rise. I'm putting 48 volt rise in. I'm getting 48 volts a drop. 12 here, 12 here, 24 here. All voltage drops present and accounted for. Make sense? Okay, so this is cool. It's really going to work like this. But we don't know the math. We don't know what values of resistance to use here. This is where it gets tricky. This is where there's another thumb rule. That's why you come to lecture. Okay, if the book was that good, you could be home in your underwear studying right now. And I could be home in my underwear correcting your work. Instead, here I'm dressed up wearing lab coats, you're wearing lab coats, and we're having this interactive lesson. The thumb rule is, you ready for this? The bleeder current needs to be 1/10 of the total load current. The bleeder current needs to be 1/10 of the total load current. How many of you buy that? You better buy it. I just sold it to you. Now the question is, what the heck is he talking about bleeder current? The bleeder current is the current flowing through the first resistor that starts the voltage division process. So by me saying that, first of all, we got to determine out what is our total load current. What's our total load current in this circuit? 28? 48? Bzz, total load current. Current is measured in amps. What is my total load current in this circuit? 10.5. What? Pounds, ounces, kilograms, amps. I love it when you talk that way. Total load current is 10.5 amps. Everybody see how we did that? The only loads in this circuit, this is a voltage divider. These are my loads. The only loads in the circuit here are, what the heck was this, a CB radio? Breaker 19 CB, right? And then this was a radar system. Radar system consumes 10 amps. This consumes a half an amp. So my total load current is 10.5 amps. Do you all agree with that? Okay. So I said the thumb rule is that the bleeder current is 1/10 of the total load current. What's 1/10 of 10.5?
1.005.
Okay. So 10.5 divided by 10, 1/10. So 1.05 amps. Do you all agree with that? Getting some puzzled looks. 1/10 my total load. 1/10 of 10.5 is 1.05. Agree with that? So that's how much current. I'm going to do something here. I'm going to change the color to make it stand out. Okay? Is going to be passing through this first resistor. Very good. Okay? And this is going to be 1.05 amps.
The book gave an arbitrary number of 10 milliamps.
And again, that's where's that coming from?
Pulled it out exactly. The text was definitely vague on that.
So at least remember my deal. So right there, we just unlocked the entire circuit. We just unlocked the entire circuit because what we've got here is 1.05 amps coming up out of this node. How much current do we have coming up through here?
1.5.
Where'd that number come from?
Printed the paperwork.
Thank you, the paperwork, okay? Or your calculation based on, if the paperwork left out the current demand, you know it's a 5-watt radio, and you again, as long as you can prove it. Got to be able to prove it to somebody, okay? So we called that 0.5. So we've got 0.5 amps coming up through here. All the current that comes up through the radio is going to come here into this node right here. So I got 0.5 amps coming in from this angle. I got 1.05 coming in from this angle. Can any tell me about how much current's going to be going through this? How'd you come up with that? And how'd you come up with that? Is that just is that a notion?
It's a current divider.
It's a current divider. It is a current divider.
The node they have to combine again.
Okay, but again, what's going to bring tears to my eyes is if you quote me laws. Are there any laws that govern what's happening here in this node? What is it? Absolutely. Kirchhoff's law. I got 1.05 coming up here. I got 0.5 here. We got a traffic cop standing in the middle of that intersection. How much current's driving away from him? 1.55 amps. It's gotta. It's gotta. If this thing's functioning, it's gotta work like this. So I've got 1.55 amps coming up through here. Okay. How much current is coming up through this load? How do we know that? Placard data, technical documentation, calculation utilizing Watt's law. I don't know. Because Joe said so. Actually, I didn't. All I gave you is that 24 volts and the 200 watts. You folks really calculated that out. The only curveball that I shot you in any of this was the efficiency bit. I'm talking about efficiency. The book doesn't even talk about that. But you don't get 100% of anything. You don't. There's nothing that's 100% efficient. So I got 10 amps coming up through my radar system. That means that 10 amps makes a 90-degree corner at the speed of light. Right? 10 amps.
11.55 amps.
How do we get an extra amp?
How'd you get an extra amp with what?
Well, we got 10, we got 0.5 amp, half an amp.
What was the rule here? What was the whole thing on unlocking this entire circuit? What did I call this resistor? The bleeder resistor. And that's what's starting the whole process. We have to have some current going through that to create. And the reason that we use 1/10, so is that these loads come on and offline, the circuit's going to have stability because that CB is not always going to be on. And when we turn the CB off, we don't want the whole circuit to go cattywampus. We want it to be somewhat balanced. Same thing with the radar system. So it's a thumb rule. It's not an absolute, it's a thumb rule that should give us consistency of operation for this circuit. Make sense? So we know that we have 11.55 amps coming up through here. Boom. If I've got 11.55 amps flowing into my power supply, how many amps must I have flowing out of my power supply? The same. Okay? So that means I've got 11.55 amps flowing into this node. If I've got 11.55 amps flowing into this node and 1.05 amps flowing out of this node, how much current do I have flowing in this direction?
10.5.
How much? 10.5 amps. Do you agree with that? If I've got 10.5 amps flowing into this node and I got 0.5 flowing in this node, how much current am I going to have flowing in this direction? Isn't that the same number we started off with? So I just proved that this works. I just traced all the current through this circuit in doing this. Now, the easy part of the analysis VIR, let's calculate out resistance, voltage over current. Voltage over current, right? Voltage 12 over 1.05. 12 over 1.05 is going to give me this value of resistance. R is going to be equal to
14.40 volts.
$11.428 ohms. That's what I came up with. Are we going to find 11.428 ohm resistor?
No.
Can we find something close? Maybe we could find one with tolerance as a 10 ohm resistor that's on the high side, 20% tolerance. We could find one that's within that, right? Because a 10 ohm resistor could be anywhere from 12 ohms to 8 ohms. So yeah, we might be able to find something close to that. It's not going to be that critical.
What happens if your resistor only actually has 8 ohms if you get that big of a tolerance?
You're going to get less of a voltage drop there, so that is kind of critical.
Higher up than lower?
the bigger the resistor, the bigger the voltage drop. The smaller the resistor, the smaller. So we can do the same thing up here, right? 12 volts divided by 1.55 amps. 7.7 ohms. And then finally here up at the top, 24 divided by 11.55. 2.08 ohms. And this is how you analyze a loaded voltage divider. It's really nothing unique, is it? All we did is apply Ohm's law, Watt's law, Kirchhoff's law. You know, one of the other things that's kind of fun that I could do with this circuit, I think it's fun. You'll probably think I'm horrible for doing that kind of stuff. What is it? It's the exact same circuit. And to be honest with you, this is how this thing would really be connected. This is how it would be really connected. Your 48 volt power supply would be connected to what kind of ground? Electrical ground. Not necessarily earth ground, electrical ground, which is typically a chassis ground or a frame of a vehicle or a boat, the hull of a ship, right? The frame of a train car. This is how it's going to be done, because we're going to use the frame as a conductor. Circuit's going to operate exactly the same. We're going to get the bottom of the circuit here, the bleeder resistor, connect that also to ground, chassis ground. Okay? We're going to connect the negative lead of our radio directly to chassis ground. We're going to connect the negative lead of our radar. The radar's kind of mounted in an unusual position, you know. I got that, you know, the pulpit up there, I drive the boat, I want the little radar there. So I'm going to have to run quite a bit of cable, but I'm still going to connect it to chassis ground. And this is the exact same circuit that you just analyzed. I just made it more complex, complicated looking by putting these grounds in. Basically, when you see this in a circuit, you know that electrically all of these, wherever the heck that thing is, right, all of these are interconnected. Don't let me screw you up with this kind of stuff. And it's assumed that you know how to interpret this type of stuff. Questions?
With the beginning part where you need to figure out the meter current,
Yeah.
take the total current, which is 10.5, and divide that by 1/10.
Yep.
Well, I'm not coming up. It comes up with 105, not 1.05.
10.5 divided by 10.
Oh, divided by 10.
1/10 is 10, right? 1/10 is 10. Make sense? 10.5. 1.05.
You can multiply it by 0.1, you get the same answer.
10% of 100.
Another question? No? Questions? So you could sit here, and again, that's a thumb rule, but you could use it for analysis. And then if somebody asks you, how the heck did you come up with that? How did you, what, you want me to buy these parts? How'd you come up with that? Well, I used it as a thumb rule that I want my bleeder current, oh, okay. As opposed to the author who just, again, I don't know where those numbers came from. I don't know, I don't want to know, it is what it is. So in the future, use that 1/10. I use that 1/10, you're not even going to get the, I mean, you won't get the answer that the author gets in the book. I don't know what you got to do it wrong to get the number that the author gets in the book. So this, in the future, when you see loaded voltage dividers, use that 1/10 rule, unless you're told otherwise. You know, there might be an engineer that knows a lot more math than we know. They say, no, we want you to assume 15% or 20% or whatever. But you need some guidance. We're not engineers. You guys remember that? You know that? We're not engineers. Anybody here want to be an engineer? Honestly? No offense, honestly. Okay? If you want to be an engineer, that's good. You're going to immerse yourself more in the world of theory. We immerse ourselves more in the world of reality. So we're going to do what we're told to do. I actually had a meeting today with engineer. We're looking at some engineering starting some engineering classes here at Lake Washington, a parallel program to pursue your engineering degree. And the way he was talking about it, too, like a pyramid. It's like a pyramid. You get your research science, a handful of research people up here at the top of the pyramid. Then you've got engineers designing the stuff. And then you've got technicians making the stuff work. So there's a lot more technician jobs out there to support engineering, and the engineering supports R&D. You know, Boeing only has a handful of people that sit around and think about weird crap all day long. Thank God, right? Because then what they do is they farm it out to the engineers and say, hey, make this work. Make this work. And then the engineers figure it out, the calculations and everything, and then they give it to the technicians and they say, make this work. And then we are the last line of defense. And the only thing that we have to fall back on are the laws of physics and the theory of operation. That's all we have to fall back on. And if you can apply that, then you're going to be ahead of the game. There's no question about it. No question about it.